What if I told you that the number 0.5, a number you interact with and rely on literally every single day, uh, actually does not exist as a clean decimal in half of the mathematical universe?
I mean, when you put it like that, it sounds totally absurd.
Right. Or like that the visual symbol we use to represent it is currently at the center of this massive digital accessibility war.
Yeah, we really just think of splitting something down the middle as the ultimate expression of simplicity. I mean, you have a dinner bill, 2 credit cards, you split it, it's perfectly fair, perfectly symmetrical.
But the moment you look at the actual mechanics of what it means to divide something in two, that clean split becomes a massive rabbit hole. So, welcome to today's deep dive. Our mission today is to take something you probably haven't thought twice about since, well, elementary school math, the fraction 1/2, and put it right under a microscope.
Because 1/2 isn't just some basic fraction, right? It is a literal and figurative balancing point across like multiple disciplines.
Exactly. And by the end of this deep dive, you are going to realize that something as mundane as splitting the bill sits at the absolute center of million-dollar mathematical mysteries, bizarre linguistic anomalies, and even the way our computers render text.
Yeah, we've got a really great foundational text here that breaks down the math, the language, and the typography of this completely ubiquitous fraction.
It's the perfect example of how the concepts we take the most for granted usually hide the most complexity when you actually stop to examine their moving parts.
Absolutely.
Okay, let's unpack this, starting with how we even talk about it. Because before we can even get to the math of a half, we have to look at the word itself. The English language completely breaks its own grammatical rules just to accommodate this one specific fraction.
It really does. So let's look at fractions as a whole. Mathematically, 1/2 is the multiplicative inverse of 2. It's an irreducible fraction. You have a numerator of 1 and a denominator of 2, and you can't simplify it any further than that. But linguistically, the way we name fractions usually follows a very predictable regular derivation based on ordinal numbers.
Right, yeah. Like if I divide a pizza into 6 slices, one slice is a sixth.
Exactly.
If I divide it into 7, it's a seventh. Fourths, fifths, tenths, hundredths. The rule is incredibly consistent. You just take the number, slap a th on the end, and you have your fraction.
But if we divide that same pizza into 2 pieces, we absolutely do not call one piece a second. We call it a half.
Which is such a weird anomaly. I mean, it's a linguistic phenomenon called suppletion. For you listening, the best analogy to understand suppletion is how we have completely different, unrelated words for irregular past tense verbs.
Oh, that's a good comparison.
Right. Like, we don't say, I go to the store. We say, I went. And the word went has absolutely no etymological connection to the word go, but it hijacked the past tense spot anyway.
Yeah, it just forces its way in.
Exactly. The word half does the exact same thing to the fraction of 2. It just barges in, completely ignores the th rule, and replaces 1 second.
What's fascinating here is why language does that. Irregularities in a language aren't random. They are almost always driven by frequency of use.
Oh, really?
Yeah. The words we use the most constantly, like the verb to be, for example, are the most irregular because they get locked in so early in human history, and because they're used so much, they resist the standardizing forces of language evolution over time.
So because early humans were breaking things in two long before they were calculating, sixths or sevenths, the concept was so deeply ingrained it just kept its ancient, unique root.
Exactly. It shows just how foundational the concept of having is to human communication. And functionally, our text notes, it operates uniquely too. It can be hyphenated as a compound word like 1/2, or just used to describe one part of something divided into 2 equal parts.
Well, let's move from how we speak about a half to how we actually calculate it. Because looking at the arithmetic of 1/2 leads to a really surprising realization about the mechanics of the number systems we use every day.
Yeah, let's start on the standard number line. 1/2 sits exactly midway between 0 and 1, and its inverse operations are completely tied to the number 2.
Meaning, like, if you multiply a number by 1/2, that is mechanically the exact same thing as dividing it by 2. You're halving it.
Right.
And conversely, if you divide something by 1/2, you are mechanically multiplying it by 2. You're doubling it.
Which is a really beautiful, clean symmetry, but the way we represent that exact midpoint gets complicated when we look at decimals.
Oh yeah, this part blew my mind.
Because in our base 10 system, the way we count normally 1/2 has 2 entirely different mathematically valid decimal representations.
The first one is the one we all know, 0.5.
Right. But the second one is a recurring decimal. 0.4, followed by an infinite string of nines. 0.4999, repeating forever.
Wait, hold on. I need to push back on that. How can 0.49 repeating, going on forever, be exactly 1/2? I think a lot of people listening would intuitively say, well, it gets infinitely close to a half, but it's not actually the exact same thing as 0.5.
Yeah, that's a very common intuition to think of it as just approaching the number. But mechanically, they are mathematically identical. It relies on the mathematical proof that 0.999 repeating is exactly equal to 1.
Okay, walk me through that mechanism, because that sounds crazy.
Think about the fraction 1/3. In decimals, 1/3 is 0.333 repeating, right? If you multiply 1/3 by 3, you get 1.
Yep.
But if you multiply 0.3 repeating by 3, you get 0.9 repeating. So 0.9 repeating must be exactly equal to 1. There are just two different ways of writing the exact same value.
Okay, I see. So if you divide the number 1 by 2, you get 0.5. And if you divide its exact equivalent, 0.9 repeating by 2, you get 0.49 repeating.
Exactly. They are two valid, exact decimal representations of the exact same midpoint. And this pair of expansions, a clean terminating decimal and an infinitely recurring string, this happens for the number 1/2 in any even-numbered base system.
Which brings us to the craziest part of the text we're analyzing. We use base 10 because humans evolved with 10 fingers.
Right.
But what happens if we step outside of an even-numbered base system? Like, what if we used an odd base, like base 9 or base 7?
Well, if we operated in an odd base system, the concept of 1/2 would have absolutely no terminating representation at all.
Wow.
It is mathematically impossible to write down a clean finished decimal for a simple half in an odd base.
That is staggering. Let's break down the why for the listener. Why does base 10 give us a nice clean 0.5, but base 9 breaks down completely?
It all comes down to prime factors. In any base system, a fraction will only result in a clean terminating decimal if the denominator's prime factors match the prime factors of the base itself.
Okay.
Our base is 10, the prime factors of 10 are 2 and 5.
So because the denominator of 1/2 is 2, and 2 is a factor of 10, it divides perfectly into a clean 0.5.
Precisely. But let's look at base 9. The only prime factor of 9 is 3. 2 is not a factor of 9. So if you try to divide a whole unit by 2 in a base 9 system, it literally cannot resolve.
It just breaks.
Yeah, it will instantly turn into an infinite repeating decimal, just like dividing by 3 does in our base 10 system.
So, okay, if I'm an alien with 9 fingers and I want to write down the decimal for exactly 1/2, I would have to write 0.44444, trailing off into infinity.
Yes, exactly. In base 9, 0.4 repeating is exactly 1/2. So our comfort with the clean, precise 0.5 isn't an inherent property of the fraction itself.
That's wild.
It is merely a lucky byproduct of the fact that 10 happens to be divisible by 2. The universe's fundamental midway point doesn't care if our specific decimal system can neatly contain it or not.
Here's where it gets really interesting, though, because if we step away from the abstract rules of base systems and look at physical space, like at geometry, we can actually see what this concept of infinity inside a half looks like.
Oh, definitely. Geometry relies heavily on the concept of a half. I mean, the most basic example is that the area of any triangle is exactly 1/2 its base times its height.
Right, but the visual that really grabbed me is the infinite square. I want you to picture this with me. Imagine a perfect square sitting in front of you, and its sides are exactly a length of 1. So it's a 1 by 1 square.
Okay.
Now, take a pair of scissors and cut that square exactly in half. You now have 2 equal rectangles. Put 1/2 aside. Now take the half you have left and cut that exactly in half.
So now you have a quarter.
Exactly.
Uh-huh.
Put that aside. Take the remaining piece, cut it in half again. Now you have an 1/8. Then a 16th. A 32nd.
If we connect this to the bigger picture, what you are doing is dissecting that 1 by 1 square into a geometric progression. You are creating rectangles whose areas are successive powers of 1/2.
And you just keep slicing that remainder in half, like into infinity. You will physically never run out of pieces to cut, because you can always have what's left.
Right.
But if you take all those infinite microscopic pieces and push them all back together,
they will perfectly reform that original 1 by 1 square. It is a strict geometric proof of how an infinite series of fractions, halves, quarters, eighths, extending forever, can sum up perfectly to a finite boundary. In this case, the number 1.
It's mind-bending. You have an infinite number of physical actions, an infinite number of pieces, but they completely fit inside a single closed square.
It's a beautiful visual.
And that geometric progression, that idea of successive powers of a half, actually leads us straight into the deepest, most complex echelons of theoretical math.
Yeah, we are moving from the very tangible cutting of a square into some serious high-level abstraction here. But even in the highest spheres of math, 1/2 remains a foundational pillar.
Let's start with exponents. We just talked about successive powers of a half. If you raise a number to the power of 2, you square it, right?
Right.
5 to the power of 2 is 25.
Right.
But what mechanically happens if you raise a number to the power of 1/2?
It equals its square root. So 25 to the power of 1/2 is 5.
Which feels totally counterintuitive.
Right?
Why does raising something to a fraction suddenly turn it into a square root?
It follows the core logical rule of exponents. So when you multiply two identical base numbers together, you add their exponents. For example, x squared times x cubed equals x to the 5th power. You just add the 2 and the 3rd.
Great, I follow that.
So apply that same logic to a half. A number to the power of 1/2 multiplied by that exact same number to the power of 1/2 equals that number to the power of 1. Half plus half equals 1.
And the definition of a square root is the number that, when multiplied by itself, gives you the original number. So x to the power of a half must be the square root. That is incredibly elegant.
It really is. But the elegance of 1/2 goes far deeper than basic exponents. The text brings up some absolute heavyweights in pure mathematics. For example, the gamma function.
I'm going to need you to explain the gamma function to me like I'm 5, because just reading the name makes my palms sweat.
It's not as scary as it sounds. Think of a factorial. 5 factorial is 5 times 4 times 3 times 2 times 1. It's a way of multiplying a descending sequence of whole numbers.
Okay, sure.
But mathematicians wanted a way to calculate factorials for numbers that aren't whole integers. Like, what is 2.5 factorial?
Oh, wow.
Yeah. So the gamma function is a complex equation that draws a continuous sweeping curve connecting all those whole numbers, allowing you to find the factorial of decimals and complex numbers.
Okay, so it's basically a factorial calculator for the spaces between the whole numbers.
Exactly. And when you evaluate the gamma function at exactly 1/2, the exact midpoint between 0 and 1, the output is the square root of pi.
Pi, the circle number. Just randomly showing up inside a factorial curve because we asked it for a half.
Well, it's not exactly random. It has to do with the geometry of the curve mapping back to a Gaussian bell curve, which inherently contains pi in its area.
Right.
But yes, it's a beautiful mathematical surprise. The material also mentions the Bernoulli numbers, specifically the value b sub 1.
And what are the Bernoulli numbers?
They are a deeply complex sequence of rational numbers that pop up everywhere in calculus and number theory, especially when you are trying to sum up infinite series of powers. It is an infinite sequence of numbers.
Right.
But b sub 1 is entirely unique. Depending on the mathematical convention you are using, its value is exactly positive or negative 1/2. It is the only Bernoulli number with an ambiguous sign, sitting precisely at that fulcrum point.
Which brings us to the biggest heavyweight in the material, the Riemann hypothesis. For those listening who aren't deep in the math world, the Riemann hypothesis is literally $1 million problem. The Clay Mathematics Institute will pay you $1 million if you can prove it. It is arguably the most important unsolved problem in pure mathematics because it is believed to hold the secret blueprint to how prime numbers are distributed across the universe.
And what is the specific conjecture at the heart of the Riemann hypothesis?
Well, the conjecture states that every non-trivial complex root of the Riemann zeta function has a real part equal to exactly, you guessed it, 1/2.
Exactly 1/2.
But let's demystify that jargon. What does it mean for a real part to equal a half?
The Riemann zeta function is a function that takes complex numbers, which are numbers made up of a real standard number and an imaginary number, and maps them to other complex numbers. You can visualize complex numbers on a 2D grid. The real part is the horizontal x-axis. The imaginary part is the vertical y-axis.
Okay, I have the graph in my head.
The hypothesis is searching for the zeros or the roots of this massive prime number predicting function. And Riemann hypothesized that if you plot every single one of these infinitely complex roots on that 2D grid, they won't be scattered randomly.
No.
Every single important one will land perfectly on a single, straight, vertical line.
And that vertical line crosses the horizontal axis at exactly 0.5.
Yeah.
1/2.
Yes.
So I have to ask the driving question here.
Yeah.
Why? Why does this specific elementary school fraction 1/2 keep showing up as the magic number in these massive universe-explaining frameworks?
Well, think about balancing a perfectly asymmetrical mobile or finding the exact harmonic node on a guitar string. In mathematics, 1/2 is the ultimate point of equilibrium. It is the exact center of the unit interval between 0 and 1. When you push math to its absolute most complex limits, whether you're smoothing out factorials with the gamma function or searching for the hidden rhythm of prime numbers in the Riemann hypothesis, you are ultimately looking for the system's axis of perfect symmetry. 1/2 is the mathematical embodiment of that equilibrium.
It's the exact balancing point of the mathematical universe.
Precisely.
Okay, we've traveled from the evolution of ancient linguistics through the bizarre mechanics of odd-numbered base systems and into the highest million-dollar spheres of theoretical math. But I want to bring this deep dive back down to earth.
Let's do it.
In fact, I want to look at the literal screen you are using to listen to us right now, because our sources highlight a massive modern debate about how 1/2 is coded into our digital devices.
Yes. We are talking about the typography and the digital encoding of the fraction itself.
Right. So in the world of computer characters, the 1/2 symbol actually has its own precomposed Unicode character. It lives in the Latin 1 supplement block. It renders as what's known as a vulgar fraction, which just means the common everyday way of writing it. It's a beautifully formatted single character, a tiny 1, a slash, and a tiny 2, all squeezed perfectly into the space of a single letter. You've definitely seen it.
Oh, yeah. This specific condensed typesetting has a very rich history in print, long before computers were even a thing. Our text notes a 1940 Irish postage due stamp for 1 halfpenny as a great historical example of this.
Oh, what?
Yeah, typographers designed it to look elegant, balanced, and most importantly, to save precious physical space on the page.
So what does this all mean for us today? Well, here is the fascinating problem. We took this elegant, space-saving symbol from 1940s printing presses and hard-coded it into our modern Unicode standard. But the material points out a major fundamental flaw with doing that on digital screens.
Because that precomposed character forces 3 separate visual elements, the 1, the slash, and the 2, into a single, tiny character space. The reduced size makes it highly problematic for digital accessibility.
Exactly. For readers with even mild visual impairments, or for people using screen magnifiers, that elegant little symbol doesn't look like a half. It just turns into an illegible, pixelated blur.
This raises an important question, and it's a friction point that UI designers battle constantly. How do you balance established visual design standards with actual, functional, human accessibility?
And in this case, the modern recommendation is to avoid that elegant precomposed character entirely. The decomposed forms, which just means typing a standard-sized 1, a standard forward slash, and a standard-sized 2, are vastly more appropriate and readable for the general public.
Even if typographers think it looks clunky.
Right.
It's highly ironic. A special Unicode character designed to perfectly represent a clean equal split actually creates a barrier that divides the people who can read it from the people who can't.
That's such a good point.
It's a great reminder that technology really must serve the user's practical needs first, not just an aesthetic ideal of balance.
Which brings us to the end of our journey today. We started this deep dive with a really simple premise, just splitting the dinner bill. But look at the mechanisms we uncovered.
It's incredible.
We explored the linguistic phenomenon of suppletion that forces us to break grammar rules and say half instead of second. We broke down the mechanics of prime factors, proving that getting a clean 0.5 decimal is really just a lucky break of our base 10 system.
We visualized an infinite progression of rectangles fitting perfectly inside a single finite square.
We tackled the million-dollar Riemann hypothesis and saw how the exact center of gravity for prime numbers sits on a vertical line at 1/2. And we ended with the very real, modern problem of Unicode accessibility on the screens right there in our pockets. Those common things, the concepts we interact with every single day without a second thought, are almost always the ones hiding the deepest complexity.
They are the structural beams holding the rest of our logic together.
Absolutely. But before we sign off, I want to leave you with a final thought to mull over. Building on those arithmetic operations we discussed earlier, remember how we established that mechanically, dividing by a half is the exact same thing as multiplying by 2?
Yes, the inverse operation. Dividing by a fraction is doubling.
Think about how deeply that mathematical truth challenges our everyday instinctual understanding of less and more. We are completely conditioned to believe that that the act of fractioning or cutting something inherently makes it smaller.
Right.
But here is a mathematical reality where the act of dividing by a fraction mathematically results in an explosion of growth. It makes you wonder, where else in your life does that intuition fail you? Where else might taking a fraction of something or relentlessly cutting something down to its absolute core actually be the exact mechanism that doubles its impact?
That is a very provocative thought. Sometimes the act of reduction is the exact catalyst required for expansion.
Next time you're splitting that restaurant bill, just remember, you're not just doing basic math. You're holding a piece of geometric infinity, the balancing point of a million-dollar mystery, and an ancient linguistic anomaly right there in the palm of your hand. Keep digging, keep questioning, and we'll see you on the next deep dive.